Go.
Hello, my dear students, and welcome to our laboratory. Today we're going to continue looking at properties of water, but we're going to look at properties of solid water, specifically ice. And I want to show you some phenomena associated with ice. And the first thing I'd like to do is, I already lost my ice, is use some ice and talk about one of its main properties, and that is that ice floats on water, okay? It's less dense than water. That's a very unusual property. Ice floats in water. You want to zoom in on this? Or does it? Oops. It sunk to the bottom. Let's try that again. Ah, there's the ice we know, floating in the water with a lower density than water, so it floats. Now, one of the things I want to ask, and one of the things we're going to talk about in our discussion, is what happens when ice forms inside a living organism. Well, I have two samples of lettuce. This one I put in the freezer, and at the end of our talk, and I'm going to keep this short, we're going to look at that lettuce, and after it thaws out a little bit. And here's some fresh lettuce, spinach, different leaves, from the refrigerator that has not been frozen. This sample's been frozen, and it's frozen together. I'm afraid it's going to be a while before it thaws, but I think you'll get the idea here in a minute. Let me move these two density of ice ethers away and come over here for our third phenomenon dealing with ice, and that is, what kind of temperatures can we expect if we have ice in a polar environment? And by polar, I mean Arctic or Antarctic environment. So I'm pouring some water with some ice here, and then I'm going to add some salt to some ice here and get this ice good and coated with salt, and pour a little water on it, and then add a little bit more salt by way of adding salt to the system. Some of you may have made ice cream and know that you add salt and ice to make your system extremely, extremely cold. Trying to get another ice cube in the water so that we get that very, very effective cooling. This ice has already started to stick to itself. So let me try that again now that I've disrupted it. This is just plain old Walmart salt, and I'm going to put it on the ice and keep it there so that it helps that ice undergo a phase transition. It's going to melt it, but as it does, it's going to absorb energy from the system, from the water, and lower the temperature of the water. And this is just some alcohol. I'm going to pour it over the ice. And then here in a minute, we're going to measure the temperature. Now, if I measure the temperature, I'm going to take several of our thermometers. They're beautiful red alcohol thermometers. I'm going to let them equilibrate with these systems. And we're going to look at these temperatures that we're reaching when we set up the thermometers with these different combinations. And this speaks to the high heat capacity of ice. It speaks to the latent heat of melting. Phase transitions are accompanied by thermodynamic changes, and we're measuring that as well. And I just want to make a point about ice water and the temperature of water under the poles. So if we can zoom in on the thermometer, and if I can get these equilibrated, we'll read those temperatures and then we'll be done. I need to put on reading glasses to read the fine thermometer. But here, thermometer and ice, and if you look, I've gotten it down to about 5 degrees. Usually ice water that's become completely equilibrated is more like 4 degrees. And this thermometer is reading 4 degrees now. And I don't know if you can see that. I'll try and rotate around, but you know, we have it as good as we can get, but you'll have to trust me, it's 4 degrees. You're welcome to come in and play this or try this at home with your own thermometers. Now I have a thermometer in this ice salt bath, and if you look, this thermometer, and if you look, this beaker has condensation on the outside. This beaker, when we did this earlier, had condensation that then froze on the outside and had ice on the outside of it. And if you look, it's below 0. My temperature is minus 4 degrees in this ice salt bath. And you can get temperatures even lower if you work your system right. I can't really get the thermometer into the camera angle without taking it out of the water, but you can see here's 0, and my temperature level is well below 0. In fact, right now it's about minus 6 degrees, so quite cold. And then here's my ice and alcohol bath, and it has a temperature of, it's still above 0, but I need to stir that up and get some of the cooling effect of the melting ice. And as I do this, I'm headed below 0, a couple of degrees below 0. Let me get the same kind of thermometer so we don't have to change how we're reading them. And this is getting much colder. It's headed down. It's at 2 degrees now. It's at 1 degree now. And if I let this ice alcohol mixture go, it is now below 0. If you see, it is about 1 or 2 degrees. It's just barely 1 degree below 0. So, you can achieve temperatures below freezing by taking advantage of that phase change, the solid to liquid phase change, where the ice absorbs heat to make that change. This one's minus 7 now, and it takes that heat. Where does it get the heat? From the water. So the water's going to go and be colder. The solution's going to be colder. Now, why doesn't this water freeze? Because it's full of salt, and salt does something called freezing point depression. This is an alcohol water mix, 70% propanol, isopropanol, and 30% water. So this isn't pure water either, and it is now minus 1. So let's go back to our lettuce. It hasn't really thawed yet. We're not going to wait for it to thaw, but it's starting to thaw, and I don't know if you can see, but this poor lettuce is like wilted lettuce. It has had, it's leaking and turning things. You can see the chlorophyll is there because the cellular structure has been disrupted. As the tissues froze, ice crystals cracked through the cells and cracked through the membrane. It's not that the cells swelled up because ice has lower density and greater volume when it freezes. It was actually ice crystals and ice needles forming that penetrate the cell and break it from the inside and the outside. Those plant cells have the ability to swell up and grow what we call more turgid or more rigid. That's what happens in the grocery store when they spray water on the vegetables to make them look fresher. They absorb that water and swell up and don't look so wilted. But freezing for most organisms kills it. In the discussion, we'll discuss some others that don't die upon freezing. So this concludes our lab and our lab demonstration and our playing with ice and water. But the next video will have a quick screencast of the discussion and help you with some of the questions, with answers to some of the questions, most of the questions on the lab report. So until then, stay safe and goodbye now.